everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new topic called direction cosines, which will tell us the direction of a straight line. So we've already seen many different forms of a line when you talk about it in terms of two dimensions. So let's say this is the x and y axis. This could be a line. Then the equation of this line could be something like y is equal to mx plus c. Now if this is the format of the line, then m would be the slope of the line and c would be the y-intercept, because when x is 0, c is equal to y. So this is one form. We studied many other forms. You could have two points given, x1 y1 and x2 y2, and a line through them. You could have one point and the slope given, and you could write a line through that. So there were many formats, but the equation for all of them was the same. For a single value of x, you got one value of y in general. So if you just draw a line parallel to the y-axis here, this is a particular value of x, let's say 5. You put x is equal to 5 here, you get a particular value of y. That is the property of a line in 2 dimensions. Similarly, the property of a line in 3 dimensions, we just have to generalize it quite naturally. So I'll have a little bit of trouble drawing a line in 3 dimensions. Let's say this is a line which is not just in the plane of the viewer, it has some z component as well. This is x, y and z. Once again, you can see x cross y will be equal to z always, because we will use the right-handed coordinate system. So now let's say you draw a line parallel to the y-axis, and here you have a particular value of x. Right, you draw it at z is equal to 0. And so for a particular value of x, you get a particular point. You don't get any more than one point, right? Unless this line is parallel to the y-axis or some special cases. For a single plane like this, you get one particular point. That means for a particular value of x, you get that x and then y and z. So this is the generalization to 3 dimensions. Every value of x gives me one value of y and one value of z. So that immediately removes equations like this of the table. Y is equal to mx plus mx plus let's say lz plus c. This can't be an equation, because for a particular value of x, we get a relationship between y and z. We don't want that. That's not a straight line. A straight line tells me for a single value of x, we get one value of y and one value of z. So before looking at the specific equation of a straight line, let's look at some properties which will be useful. The first property of a straight line is called its direction cosines. A direction cosine is somewhat similar to the generalization of a slope in 3 dimensions, though there are some differences. So we know what a slope is already. Let's say this is a line in 2 dimensions. This is the y-axis, the x-axis. So this would be, let's say, the line y is equal to mx plus c. So it has a slope m, which basically denotes the direction of this line. It literally is equal to tan theta, where theta is the angle made with the x-axis. So if we were to extend this theta, so the slope would be equal to tan theta, but it tells us the direction. If theta is 0, tan theta is 0, meaning the slope is 0. So the slope is 0 if the line is parallel to the x-axis, and the slope is infinity if the line is parallel to the y-axis. Right. Now it can also have a component in the z direction, and that's when you start using the component of direction cosines. So the direction cosines basically are the cosines. Cosines basically means the cos of the angles made by the line with the x-axis, y-axis and z-axis. So any two lines, if they're intersecting, will have some angle between them, right? So the cosines of the angle made by any line in 3 dimensions with the x, y and z axis. So let's say the angle made with the x-axis for a line is alpha, the angle made with the y-axis is beta, and the angle made with the z-axis is gamma. Then the direction cosines, often referred to as DCs, will be cos alpha, cos beta, cos gamma. it's a set of three numbers basically. A direction cosine is a set of three numbers. Each number obviously will lie between -1 and 1, right? And it is a way of denoting the direction. Now, the direction cosines don't determine the line uniquely. Two separate lines may have the same direction cosine. For example, y is equal to mx plus c. If we have y is equal to mx plus 2 or y is equal to mx plus 7. One line might be like this, the other line might be like this, but both of them have the same slope. So the slope is one property of the line. It tells us the direction of the line, but it is not enough to uniquely determine the line. We also need something else, either one point through which it passes through, or the y-intercept, or the x-intercept. We need some other information. Similarly, the direction cosines determine the direction, but it is not enough to determine the line completely. We also have to have some other thing so that we can determine the direction. So that we can determine the line uniquely. Now, just like if we needed the slope of this line or the slope of this line, y is equal to mx plus 2, y is equal to mx plus 7, y is equal to mx would still have the same slope. That would be a line passing through the origin. Right. And when it comes to the angles made with the x, y and z axis, it's easiest to see them when you pass a line through the origin. So obviously for the direction cosine, you can just assume that the line passes through the origin. That will be one of the infinitely many lines having those direction cosines. There will be other lines as well, but it's easy to see the angles made with the x-axis in terms of passing it through the origin. So let's look at the direction cosines of a few two-dimensional lines just to make us comfortable with this topic. So let's say we have a line which has m is equal to 1 by root 3, let's say. M is equal to 1 by root 3 means this angle is 30 degrees, right? Because tan theta will be 1 by root 3 and theta is 30 degrees. So the angle made with the x-axis is 30 degrees. What is the angle made with the y-axis then? It is 60 degrees. And what is the angle made with the z-axis? Well, this is the z-axis. Let's say this is the z-axis. So the line lies in the xy plane. It does not have any z component. In fact, we are actually looking at a two-dimensional line, right, in two dimensions. So the angle made with the x-axis alpha is 30. In this case, the angle made with the y-axis beta is 60. The angle made with the z-axis gamma is 90 degrees. And this is true. You'll need to think about it a little bit. Just pick up a pen and a paper and try to do it yourself. You take any line in the xy plane, it will always make an angle of 90 degree with the z-axis. The x-axis makes an angle of 90 degree with the z-axis. The y-axis makes an angle of 90 degree with the z-axis. Any line in the xy plane will make an angle of 90 degree with the z-axis. In fact, all two-dimensional lines which you've seen up till now of the form y is equal to mx plus c make an angle of 90 degree with the z-axis. So these are the three angles, which means what are the direction cosines? Cos of 30 degrees, root 3 by 2. Cos of 60 degrees, 1 by 2. And cos of 90 degrees, which is 0. So these are the direction cosines of this line. Now, you could have any other line parallel to this line, whether it's this line, this line, this line. All the lines parallel to this line will have the same direction cosines, just as they will have the same slope. But they will not be the same lines because they will pass through different points. These are basically a set of parallel lines. That is one point. The other point, if it is in the xy plane, then gamma will always be 90 degree, cos gamma will always be 0. Right. If you were to take a line in the xz plane, let's say this line, which makes an angle of 45 degrees. Then the angle made with the x-axis. By the way, one more thing, when you're talking about direction cosines, clockwise or anti-clockwise doesn't matter, because cos of minus gamma is the same as cos of gamma. So in this case, the angle with the z-axis is 45. The angle with the x-axis actually is minus 45 because you are going in the anti-clockwise direction. But it doesn't matter, we'll just write 45 because the actual direction cosine is what is important. Cos of minus 45 is the same as cos of 45. And the angle made with the y-axis is obviously 90 degrees because this is a line in the xy plane. So the direction cosines of this line, which is bisecting the x and z axis in the xz plane, the direction cosines will be 1 by root 2, 0, 1 by root 2. Now let's look at a few properties regarding direction cosines. One of them is something called direction ratios. Direction ratios are nothing but a set of three numbers in the same ratio as the direction cosines. So the first line we looked at had the direction cosines root 3 by 2, 1 by 2 and 0. So it would also have this direction ratio. Another set of direction ratios could be root 3, 1 and 0. Another could be root 3 by 100, 1 by 100 and 0. Or 5 root 3, 5, 0. Right. So direction ratios are essentially, the important thing is the ratio. So it is basically any three numbers which have the same ratio as the direction cosine. So this would be the direction cosines, but all of these would be the direction ratios. Right. Some authors also call direction ratios as direction numbers. Yeah. So the direction cosines are unique, but the direction ratios are not. Also, the direction cosines have a particular property which helps us to determine the direction cosines from the direction ratios. So let's call the direction cosines L, M and N for now, right? Which means L is equal to cos alpha, M is equal to cos beta and N is equal to cos gamma. And let's say the magnitude of the R, or not magnitude, distance from the origin, let's say. Yeah, so let's say this is a point at a distance r from the origin, and this line joining O and the R has these direction cosines, right? So what will be the projection on the x-axis? This angle is alpha. The projection on the x-axis, or the x component of this vector, will be r cos alpha. Now the angle with the y-axis is beta, so the y component will be r cos beta. So we can write this as r cos alpha I cap plus r cos beta j cap plus r cos gamma k cap, right? For any vector r which has the magnitude r, if it makes an angle gamma with the z-axis, then the z component will be r cos gamma. This is something we already know from vectors, right? If this is a vector a and this is an angle theta and this is a vector b, the component of the vector a in the direction of b is a cos theta, right? The projection rather. And we know that the magnitude of this vector is r. But what is the magnitude of this vector? R square cos square alpha plus r square cos squared beta plus r squared cos squared gamma is equal to r squared, because that is the magnitude. This cancels. Cos gamma is L, cos beta is M, sorry, cos alpha is L, cos beta is M, cos gamma is N, which gives me a very important relation: L squared plus M squared plus N squared is equal to 1, which will always be true for the direction cosines. Not necessarily true for the direction ratios, but will always be true for the direction cosines, right? So this is sort of one version of cos square theta plus sin square theta is 1. That is in the xy direction. So let's say you have a line in the xy plane. This is alpha. Then this has to be 90 minus alpha. Cos square alpha plus cos square 90 minus alpha is obviously 1, because cos square alpha plus sin square alpha is 1. This is a generalization of that to the three dimensions. So if L, M and N are the direction cosines, then L square plus M square plus N square will always be equal to 1. Right? From that, what we can do is we can determine the direction cosines from the direction ratios. Let's say the direction ratios are given to us to be A, B and C, and the direction cosines will be, let's say, L, M and N. Then because their ratio will be the same, let's say it's K, we can say that A is equal to LK, B is equal to MK and C is equal to NK. These are the direction cosines. Any number, any set of three numbers in those ratios will be the direction ratios. But also what we know is that L squared plus M squared plus N squared is 1. This is only a property of the direction cosines. which means a squared plus b squared plus c squared is equal to k squared, right? Squaring and adding these three, a squared plus b squared plus c squared is equal to k squared times f squared plus m squared plus n squared, right? Which tells me k is equal to root of a square plus b square plus c square. From that I can get the direction cosines, which are L, M and N. L is equal to a by k, that is a by root a square plus b square plus c square. Then you have b by root a square plus b square plus c square, and finally c by root of a square plus b square plus c square. This is again once again similar to if you have the direction ratios or the ratio of two sides as a and b, then cos alpha will be a by root a square plus b square, and sin alpha, which is cos beta, will be b by that. So once again from this formula, hopefully you can see the natural generalization to three dimensions which we are doing. There's one small thing left about direction cosines, then we'll start looking at how to calculate direction cosines for lines, and that is the direction cosines can be negative. So this is something which I hope doesn't confuse you. Let's say this is the x-axis, y-axis and z-axis, and the line is, let's remove the z-axis for a second, it'll make the figure clearer. So this is a line in the xy plane which makes an angle of 45 degrees in the negative direction. So the angle made with the x-axis is 45 degrees, or rather minus 45 degrees if it is in this direction. So the angle is minus 45 degrees, and the direction cosine for the x-axis is cos of minus 45, which is still 1 by root 2. So it's still positive. However, if we reverse the direction of this line and instead it goes in this direction, then the angle made is not minus 45 degrees, it's actually 180 minus 45 degrees. So that will be the angle 135 degrees. The direction cosine will be cos of 180 minus 45, and now it's negative. And now the direction cosine will be minus 1 by root 2. So take care of this. If the angle is either alpha or minus alpha, it doesn't really matter. But if the angle is 180 degree minus alpha, then you'll have to put a minus sign. Finally, let's look at how to calculate the direction cosines of a line if it is given to be passing through 2 points. And I'll draw the figure for 2 dimensions, but I'll write all the equations for 3 dimensions. Is just the figure I'm having a little bit of difficulty drawing. So let's say this is P x1, y1, z1, and let's say this point is Q x2, y2, z2, and we need to find the direction ratios and the direction cosines of this line joining them PQ. Now what we can do is it'll have 3 components. The x component of PQ obviously will be x2 minus x1. The y component will be y2 minus y1, and the z component will be z2 minus z1. And we know that the direction cosines are basically, if this distance is a, let's say d would be a better letter. Let's say the distance between the two is d, then the direction cosines, or the direction ratios rather, would be d cos alpha, d cos beta and d cos gamma, and the direction cosines would be cos alpha, cos beta and cos gamma. So the x component would be d cos alpha. That is given to us to be x2 minus x1, which means d cos alpha is equal to x2 minus x1, which can also be written as d into l, where l is the direction cosine in direction. Similarly, d cos beta is equal to y2 minus y1 is equal to dm, and similarly d cos gamma z1 is equal to dn, which gives me L is equal to x2 minus x1 by d, and we already know what is root of x1 minus x2 whole squared plus y1 minus y2 whole squared plus z1 minus z2 whole squared. So x1 minus x2, y1 minus y2 minus z2 are the direction ratios, and x1 minus x2 by d, x2 y1 minus y2 by d, and z2 minus z1 by d are the direction cosines. So m is equal to y2 minus y1 by d, n is equal to z2 minus z1 by d, and d is obviously given here. So this is basically stuff which you already knew intuitively. Now we just put it into rigorous language. X2 minus x1 is the x component. The ratio of the x, y, and z component are the direction ratios. If you divide them by d such that L squared plus m squared plus L squared is 1, or they are actually equal to cos alpha, cos beta, and cos gamma, then you will have the direction cosines. In the next video, we'll learn how to write the equation of a line in three-dimensional space. Thank you.